Okay, let's start. Do you have any questions? Okay. Okay. So last time we were mainly discussing 3.1. I think you can call it conditional distribution. Discrete random variables. Okay. And we won't repeat the details, but basically the idea is given two random variables, right? X and Y. And in general, they don't have to be discrete. It can be continuous, they can be whatever. Of course, in 3.1, and a lot of times in this course, they'll be discrete, but they don't have to. The task is to be able to say what the distribution of X given Y. Okay. Well, how can you do it? The most straightforward way is by definition, but doesn't have to be always the case. So by definition, then you can, of course, write something like this. All right. But as I explained last time and with a lot of examples, this is not enough a lot of times, right? After you do this, you have to manipulate, you have to work out the calculation to be able to say meaningfully, okay, what the distribution is. Well, because Y, right? To figure out the distribution of X given Y, it's just really the step in between, because maybe the question will be something like, right? So this is to figure out the distribution of X given Y so that you can compute, let's say, expectation of X given Y or variance of X given Y, okay? Something like that. Or, even maybe something like probability, who knows? Any of these may be the, sort of like what you're looking for. And the step to get there is by knowing the distribution of X given Y. All right, for example, we got the result that if you have, let's say, XY, right, independent binomials and let's call X1, X2, right? And I, right, P, okay? I equals 1 and 2, right? Like that. Then the conditional distribution of X1 given X1 plus X2 will be what? It will be a hypergeometric, right? It'll be a hypergeometric random variable with what kind of parameter? Well, if you fix, right, the sum of the binomials, then it's like you are selecting, right? You're selecting out of n1 plus n2, right? A group of n1 plus n2. So you have n1, n2, and x1 plus x2, right? So basically you have n1 as a number of categories, right, of the first color in the urn. Like, so remember, right, the urn hypergeometric is about a model, right, of an urn with two categories, right? Let's say blue and red. Then blue, right, has so many has so many balls, and one. Red has so many colors, let's say n2, right? Has so many balls, n2. And then you select, let's say, R balls, right, out of the urn. Without replacement, right? And you try to track how many balls, right? How many blues among the R ball, right? So that's the hypergeometric. And when you have independent binomials like this, and when you condition on the sum, you exactly have the same situation, where the sum here exactly represents the number that you selected out of the sample without replacement, okay? Why? Because, you know, they represent the total number of success between x1 and x2, okay? And you're trying to figure out among those total number of successes, which is among R, how many of them belong to the first category, okay? Again, right? I mean, we're not gonna go through the calculation again because that calculation takes several lines. But we need to, or we want to be able to remember or recognize those, let's say, typical cases quickly so that we can do, you know, like a problem faster that way. And so, for example, right, to continue with the example, if you calculate expectation of x1 condition x1 plus x2 in this case, it will be, well, the expectation, right, or hypergeometric will be the ratio, right, the relative ratio of the category you're interested in. Okay, multiply with the sample size, which is x1 plus x2, right? And again, all of these are done very quickly because we recognize what the conditional distribution is. If we don't, then, you know, the task of calculating this is kind of hopeless. Another example that we did last time was what? If you have xi independent, I guess, Poisson, right? Then x1 condition x1 plus x2 will be what? Will be a binomial, right? With the total number of success as, sorry, the total number of trials as x1 plus x2, and the success rate is lambda 1 over lambda 1 plus lambda 2. Okay. Again, this is through, let's say, memorization or through intuition. To derive this expression, right, will take, let's say, several lines. But then, right, the expectation of x1 condition x1 plus x2 now will be x1 plus x2 times lambda 1 over lambda 1 plus lambda 2. One more, right? If x1 and x2 are independent geometric, P, right? Then x1 conditioned on x1 plus x2 will be uniform, discrete uniform, x1 plus x2 minus 1. Okay? And so expectation of x1 condition x1 plus x2 in this case will be, right, the expectation of the discrete uniform okay. And so, well, I mean, I don't have the discrete uniform memorized, but basically, right, it takes on every values from 1 to this number equally likely. So you can do something like sum I from 1 to x1 plus x2 minus 1. You sum all these numbers and you divide by the probability. Okay. So this one, of course, right, is number 2 in chapter 3 problem. Once again, I mean, are these immediate? No, meaning that if you haven't done these problems before, you cannot, right, figure this out in 1 second. We did all these calculations, right? It took the entire lecture last time to figure these things out. I mean, and some other stuff. But the point is, even after we have done these calculations, and especially, okay, for the typical cases that are from the models, okay, from the ones that we write down the chart for, okay, the well-known random variables, then these results must be memorized because we don't have time to go through them. I mean, unless, like I said, the question is specifically about deriving these, all right? And moreover, memorizing these results and understand why, at least intuitively, sorry, not here, right here. Will help you build the intuition that is going to be very much needed to do the problems in this chapter when you condition. Now, so to figure out the distribution of x given y so that you can compute this. But a lot of times, this will only be the middle step anyway. The last step could be, and very much will be, to compute, let's say, expectation of x, variance of x, or probability of x equals to x, whatever, less than or equal to x, by conditioning. So in other words, the last step, which is going to be one of the most popular kind of problems in this chapter, is to compute expectation and variance and possibly probability by conditioning. And it's hard because here they don't give you the random variable to condition on. You have to figure out, okay, the right random variable to condition on. But anyway, right, to show you how this step is connected to the previous steps, right, via one of the formula I mentioned last time. That is, if you condition and then you take expectation again, you get back expectation, right? This is just one formula, right? Or actually, this is the formula to use when you calculate expectation. Then you see, for example, right, in the case of the hypergeometric. So here, right, what we're doing is we apply that formula to show that actually our result makes sense or is consistent. Because if you take expectation here, right, then you take expectation of this, okay? But take expectation x1 plus x2, each of them being binomial NIP, right, is exactly N1P plus N2P. And you see, right, N1 plus N2 cancel, leaving you with N1P, which is correct because this is exactly expectation X1. So what we're just doing here is just to show that the formula is correct for this case, as long as you derive the correct expression here by deriving the correct distribution here, right? Everything is correct. Same thing here, right? If you take expectation, okay, here x1 plus x2 are Poissons. So this is lambda 1 plus lambda 2, right? But if it's lambda 1 plus lambda 2, and then you cancel with this, leaving you with lambda 1, right? And that's exactly expectation of x1. So again, right, that's correct. Finally, right, well, with the geometric, this one is tricky, okay? This one is tricky because if I take expectation here, well, it will require me, well, so I have to work out this sum, okay? This sum from 1 to n is n times n plus 1 over 2. Yeah, I can work it out, right? So this will be, right? So I have to simplify this. The sum from 1 to n, right, is n times n times n plus 1 over 2. This being n, so the answer is actually going to be just x1 plus x2 over 2, right? So the expectation of x1 given x1 plus x2 here, right, will be, right? Well, so this is just because they have the same expectation, right, which is 1 over p each. The answer will be 2 over p divided by 2, leaving you with 1 over p. So again, right, is expectation x1. All right. So these three, let's call them classical examples, they all verify, right, this formula. But of course, right, the actual application, you will have to, let's say, figure out what the random variable condition on is, okay? We'll talk more about them today. But that's just a basic review, right, of what we did last time. Any question about this? Okay. So now, let's move on to 3.3. So if conditional distribution, right, so 3.2, I think, not 3.3. You know what? I think I said it wrong. Here is 3.2. 3.1 is just general introduction. So 3.2 is discrete. 3.3 is continuous. All right. And here, I have to say that there's not as many, let's say, classical examples as the discrete cases. Well, part of the reason is this course will focus more on discrete random variables anyway. So if you work in the area where you have more continuous random variables, and there are classical examples, okay? But we're not gonna go over them as much, but you still need to know about them. So, but what's the general rule? The general rule is, by definition, so first of all, right, if you have continuous random variables, then what you have to talk about is the PDF, okay, instead of the probability distribution function or probability mass function. So you, instead of talking about conditional probability, right, like this, you talk about conditional PDF, right? So conditional PDF of x given y, right? Denoted as fx given y of little x given little y, okay, will be the joint PDF divided by the marginal PDF. Okay, that's it. So very much similar to conditional probability, okay? But now it's working at the PDF level. And once again, you have to figure out what this is if you operate a lot in this area. Bayesian statistics will have a lot to say about this kind of conditional PDF. We won't, like I said, we won't really deal with this as much, but it's still, you still have to know some of these. So let's look at, let me see here. Let's look at number 12, okay? So this is question number 12 in chapter 3. It says that the joint density is given by so this is the joint density. They asked you to show that expectation of x given y equals to y is, note, right, that this is the same as saying expectation of x given y as a random variable is just the random variable itself. Okay. So how does this work? Well, first of all, right, what do we need to calculate conditional expectation? Well, here, to calculate conditional expectation, you will need conditional density, right? So basically, here, it will be something like integrate y against the conditional density. So, sorry, this is conditional, this is x. So integrate x, all right, dx. And somehow, right, the calculation will be y itself. Okay. But of course, then you have to figure out what this is. And so the formula says, right, you use the joint and you need to divide by the marginal. Okay. And so we need to figure out the marginal density. How do we calculate the marginal density given the joint? Well, you have to integrate out the x, right? So okay, which is Oh, it's pretty simple, right? Because this is a U sub. So you get which is just eta minus y, right? And there you have it, because then the conditional density is, right, this over this, which is correct. And therefore, right, the conditional expectation is right. And well, so how do we conclude that this is equal to y? You can do integration by parts, but that takes some time. Or what else? Again, right, notice a common theme or a recurring theme in conditioning is to be able to recognize as much as possible what the conditional distribution is. So, right, I write down, we can say this is English here, what the distribution is. But do remember, right, that in between we do a bunch of calculation, we got a formula for the probability mass function of this conditional random variable, right? And then we conclude. Same thing here. When you look at this, then again, this is why you must memorize that chart of the basic random variables, because immediately you would recognize this is a what? Exponential random variable with rate y. Okay. So remember, right? An exponential lambda will have what kind of density? Right. The only thing I have to check here is, well, the calculation is correct. The only thing is depends on the class. Sometimes people call this exponential lambda. Sometimes people call exponential lambda with the lambda on top like this. Okay. Let me check. I don't remember which notation this class use. I have a vague feeling that it uses this actually. Yeah, it uses this. Sorry. Anyway, right? But if this is what we call exponential lambda, then expectation of x will be what? 1 over lambda, right? We went over this before. Therefore, so I should say this is exponential in line with the notation here. This is exponential 1 over y, right? And so we just use whatever the chart says. Exponential lambda, expectation is 1 over lambda. Therefore, exponential 1 over y, expectation is y. There's no need to do integration by parts. You just have to recognize that's the random variable. Any question? So now let's continue with kind of this theme of conditional distribution, or let's move beyond, okay, this case, which is, I think, a case that Ross doesn't discuss. But in general, you may encounter conditioning where the random variables are mixed. So you could have neither discrete nor continuous. Basically, it's a mixed type. Okay. What do I mean by this? Well, let's look at question number 13 in your textbook. All right. So basically, they say let x be an exponential lambda random variable. Again, right, this one. Then they ask you to find expectation of x condition on x bigger than 1. All right. Now, what do they mean by this? Well, I guess the meaning is quite clear, right? They just say condition on this event. What is expectation of x? On the other hand, how do we cast this, or how do we understand this in terms of the previous materials? Well, you see, right, that x here is continuous. Right? It's an exponential random variable, is continuous. On the other hand, right, what is x bigger than 1? How do we understand this? Well, the way you understand this is actually the x bigger than 1 here is, right, an indicator random variable, right? The x bigger than 1 is really about the indicator function of this random event, right? So this is the stylized 1, right, representing an event, which is what? 1 if it's true, 0 if not. Again, we've seen this before, right? In the previous chapter, which has kind of changed the notation here because this is an event associated with a random variable. So this really, right? So this random variable is a Bernoulli type, so it's discrete. So here you're asked to compute expectation of a continuous random variable condition on a discrete random variable taking on value. Okay. So that's why I say, well, so of course, this is like doesn't have to be not always the case, but it's possible right here, okay? So the point is, well, you can learn all formulas you want, but if you don't understand, let's say, how to apply the concept to certain cases, then all your formula is useless because, well, well, you can do the joint between x and this indicator function, but it's not going to be a joint density because this guy has no density. You, technically speaking, you can't really do a joint probability in the sense that you can do x equals to x because this guy is continuous, so x equal to x is 0, right? Probability 0, right? So how will we do this question? It's easier than, I advertise it to be, but I just want to point out that this kind of example, this kind of question doesn't fall nicely into the formulas that we talked about before. As far as I know, it's not listed in, the discussion by Ross. How do we do this? All right. So the first thing to recognize, right, is that X is a random variable, right? It's what's being conditioned on. You're conditioning based on this, but this is being conditioned on. So it being continuous random variable, so condition on something is still continuous, meaning that we're still looking for a conditional density here. Okay. The only thing is that it's not going to follow again, right? This type of nice formula. The reason is the Y that we're conditioning on doesn't have a density. All right, we're conditioning on a discrete random variable. Okay, so we just have to understand the meaning of it. So the meaning is quite clear, right? You know X is bigger than 1. So if you have a exponential, the density of an exponential is something like this, right? That's the density. But then you do know that actually it's not going to be overall range of values of X, but it's going to be only over X bigger than 1. So basically you cut off, right, from 1 forward, and you only look at this part. So by all kind of like things that make sense, this got to be the density, right? Except that, of course, if you look at the density here, the total mass here is not 1, right? Because it's not every area. Well, but that's kind of clear because, right, when you look at conditional density, you have to kind of divide by something, right? What are we dividing on? So we're dividing, right, by this guy, which is the probability, right? So it's a discrete random variable. So we're dividing by, so it's kind of like a mixed, right? Like I said. So you're dividing by the probability of X bigger than 1. But of course, right, the range now is going to be 1 forward. So that's the conditional density. Okay. And like I said, it's not a big deal. I'm pretty sure the moment we write this down, many folks will find that that's obvious. Okay. But the harder thing, I would say, right, is to somehow transition from, or to just recognize that this is the right answer. Okay. Because I would say that some folks will just write this down, which is wrong. Maybe some folks do some other things, I don't know. But the most common mistake is to miss this guy. Okay. But once you figure that out, then the answer is simple. And it's just an integration exercise, so I won't work it out for you. But that's how you do this kind of question. Any question? All right, let's do one more. So now we have a uniform. Okay, so how do we do this question? So it's exactly of the same type as the previous question, right? You need to find the conditional density here. And the conditional density here will be what? Will be the regional density divided by the probability of the region, right, you're in. This being the uniform, right? Then probability x less than 1/2 is 1/2. The density is 1. So therefore, so let me write this, right? Is 1 over 1/2, but what? We have the recognition that x is between 0 and 1/2 now, not from 0 to 1, because we are conditioning it. So this is actually just what? 2, 0 less than x less than 1/2. So what do we recognize? We recognize then actually here this guy has a name, right? If x condition x less than 1/2 is just going to be a uniform from 0 to 1/2. Therefore, expectation of x condition x less than 1/2 is 1/4. All right. Any question about this? Okay. So let's do one more problem. This one is just a regular discrete case, so it's not demonstrating anything, okay? But it's a question on your homework, so let's just kind of talk with a little bit. So +4. So a fair dice, right, is roll. Let x and y denote respectively the number of rolls necessary to obtain a 6 and a 5. So basically, right, hope this language is clear. We're talking about a geometric type of random variable, right? X is number of rows until you see a 6, until you see a first 6. Y is number of rows until you see the first 5. Okay. So question A, find expectation of X. I hope this is routine. What's the answer? The answer is 6, right? Because X is geometric. 1/6, right? So that's, I don't know, just a one more question maybe. B, find expectation of x given y equals to 1. What's the answer? So here, if you try to find a joint of x and y, you're in the wrong track. Okay. Again, I mean, it's just the nature of this question. Finding the joint of x and y here, you're on the wrong track. Well, you might throw this out. I don't know. Just because. Is this correct? Well, if by this you kind of try to say that this is just a representation of x anyway, then it's also wrong because, right, expectation of x given y is equal to expectation of x. I mean, there are many reasons why it can be true, but one of the most common reasons is because when x is independent of y. All right, that's one reason. If two random variables are independent, then you should remember, right, the probability of E given F is equal to probability of E if E and F are independent. Same thing here, if two random variables are independent, then, as a conditional expectation is just expectation. Well, are X and Y independent here? The answer is no. Okay. Why? Well, just think about, for example, right here. What does it mean for y equals to 1? Y equals to 1 means the first toss is a 5, right? Y equals to 1 means the first toss must be a 5. Well, if the first toss is a 5, then it cannot be a 6. Well, which is a way to say that if y equals to 1 and x cannot be 1. So y has an influence on x. Of course, the influence is way more than that, but this is just to point out that they cannot be independent. So therefore, right, throwing this out is wrong. So how do we do this? Well, it's pretty simple, really, because if y equals to 1, that means the first toss is a 5. You know that. And what is x? X is the number of rows until you obtain the first 6. But if the first toss is a 5, well, you wasted a toss. You can say something like this: it's 1 plus a geometric 1/6. Okay. Again, the reason is because, right, the first toss wasted, but then after that, you just look for the first 5. Sorry, the first 6. So therefore, right, it's geometric 1/6. That's it. So then expectation of x given y will be 1 plus 6, which is 7. All right. And again, right? So we spend some time talking about formulas and stuff like that, which has its place in this book. But one of the reasons that makes this class hard and this book hard is because a lot of problems actually won't really be formulated. You really have to understand what's going on to write down the answer. Any question? Now, to demonstrate that again, it's not as straightforward as it seems, right? The third question asks for this. And I think this 5 is coincidental, right? It has nothing to do with that 5. It might as well be a 1 or 2, right? It doesn't matter because the dice is fair. But how would you compute this? Well, first of all, is the answer going to be something like 5 plus 6, which is 11? The answer is no. I mean, because, well, where does that even come from? Right? If you, again, try to mimic this formula and hope for a right answer, well, the chance that it's going to be true is pretty slim. Okay? You have to understand what's going on to write down the answer again. So, well, what does this really mean? Y, right, is the number of times to get a 5, first 5. So what that means, right, is that for first 5 tosses, right, you know that the 5th toss is a 5. But you also know that the previous 4 tosses are what? Are not a 5. So you are only justified to write 5 plus 6, or really, right, 5 plus 1 over 1 over 6. If what you having in mind, right, is that the first 5 tosses are wasted, and then you start again, right, to search for a 6 after that. But here, right, the first 5 tosses are not wasted. Well, a 6 cannot appear here. That's true, because it's already a 5. But the first 4 tosses, just because it's not a 5 doesn't mean it cannot be a 6. All right? In other words, a 6 can appear in these 4 spots. So that's a challenge here. Okay? So this and that, or let's say very different in terms of the level of calculation. This is easy. Sorry. Expectation of x given y equals to 1. Because, right, it's a first toss. If it's not a 6, it's wasted, we just repeat. But when it moves to a 5th toss, then a lot of things can happen in the previous 4 tosses that we need to discuss about. Do we understand? And so for this kind of question, you really have to work out, right, the conditional distribution of x given y equals to 5. meaning that you have to talk about, first of all, what values it can take. Condition y equals to 5. What values can x take? Answer 1, 2, 3, 4, as we discussed, but not 5, right? And then 6, 7, 8, etc., all the way to infinity. All right. So that's the possible values it can take. Then you have to write down what the probability x equals to these values given y equals to 5. Okay. And again, these are things that you have to really think about, right? For example, what's probability x equals to 1 given y equals to 5? So x equals to 1 means the first toss is a 6, right? But then you know that the first toss that achieves a 5 value is a 5th toss. So you want a 6 here, right? But what information does that provide? It provides the information that the first toss cannot be a 5. Well, that's it, right? But if the first toss can be a 5, then among the values remaining, right, you can be a 6 with probability 1/5. Do you understand? Similarly, right? For example, probability x equals to 2 will be what? Sorry, probability x equals to 2, condition on y equals to 5, right, equals what? Well, you know this 4 tosses cannot be a 5, right? So if x equals to 2, that means the first toss is not a 6 or a 5, but the second must be a 6. So, but right, it's not a 5, so the one value is out. So the answer is 4/5 times 1/5. Right, so on and so forth until the 4th value. We understand? But what about probability x equals to 6 given y equals to 5? What would that be? Well, right, so x equals to 6 means the sixth toss, right here is a 6. Okay. But notice we don't know anything about the sixth toss. Or we don't have any restriction on the sixth toss, right? The reason is because, it's beyond the 5. Right, the first time you see a 5 is on the fifth toss. So we know the first 4 tosses cannot be a 5. But the sixth toss can be, for all we know, a 5 if you want, right? It's not the first 5 that you see. So therefore, it becomes a regular dice again, if you want to call it that. So it cannot be a 5 or 6 during the previous 4 tosses. But then, it will be a 6 here. So it will be 4/5 to the 4th times 1/6. Do you understand? So on and so forth. So basically, this is let's say a rather tedious problem to work out because you have to really divide the cases. I don't see a quick way to write down the formula or write down the answer here. But it's the nature of the problem, They place an awkward conditioning, A conditioning on the fifth toss, which makes the before the fifth toss and after the fifth toss different. So you have to really go through this analysis. But again, it's all based on understanding what conditioning means. Any question here? All right. So let me check that what I just told you is correct for part C, and then we'll continue. Yeah, that's correct. All right. Okay, any question before we continue? So again, this kind of first few questions try to give you different flavors on what conditioning means, how you find it, conditional distribution. But the real, let's say the real focus of this chapter, let's say, is something along the line of 3.5, section 3.5. Let's see if that's the, yeah, hold on. 3.4, 3.5, whatever. So we just done with 3.3, right? So 3.4, let's say computing expectations and variances by conditioning. Okay. That's 3.4.1, I suppose, which is computing expectations by conditioning. Right. And so the one single formula that will be used throughout, let's say, the chapter or even the class here, you'll see this more times than you care to know it, is that expectation of x is expectation of x given y. Okay? It's true for any paired random variables. but we will kind of try to give a proof of that, okay, for the let's say discrete and continuous case. Because like I said, right, a lot of times you don't have just pair of discrete or pair of continuous, you might have a mix. And you have seen some examples above, right, where this is true. But let's just show the proof, just again, right, try to convince you. But in general, this proof requires some more general setup, which we won't do. But what's going on, right? So proof in only two cases. So if both are discrete, okay, then probability of x equals to x given y equals to y is equal to, right, probability x equals to x, y equals to y, divided by probability y equals to y. Okay, like that. So what does it mean to have expectation of x given y? So expectation of x given y, and pay attention. The number one error, or the number one, there are several difficulties here, right? The first difficulty, of course, is to find what to condition on. We'll talk about that later. But even to execute this calculation correctly, notice there are two layers of expectation, the inside and the outside. Okay? And if you don't know where the expectation falls on, you'll get completely lost. And so even if I tell you what to condition on, you won't be able to do it. So first thing, right? The first layer, the inner layer, the conditioning, let me emphasize, is on x. Y is fixed. Even if, right, we write given y like this, y is fixed. Well, I guess exactly because we write given y. Okay, y is fixed. So expectations on x, what does that mean? Expectations on x means that you sum over the x, or you integrate over the x. All right, integrate over the x times what? Times the joint density, conditional probability. So it's going to be, well, just let me write this, right? And we wrote this formula before, right? Let's just say this. And maybe let me just write this as well, just to make things simple. Okay, which is what? Sum over all values of x, right? Whatever that is, right? That's an expression. But notice, right? So when you take this expectation, you sum over the x. But what is the result? The result after the sum, right? So you're supposed to compute the sum, right? You're supposed to do the sum in the background, let's say. But after you compute the sum, what happens? You sum over the x's, right? So the x disappears. The only thing that remains should be y. So it's going to be an expression of y. Okay, very important to know. When you take expectation, the expectation falls on the x, meaning you have to operate on the x, but the result will be an expression of y, or a function of y. So as I like to say it in short, expectation of x given y is a function of y. That's true. That's universally true. I mean, more is true about it, but at least this much is true. Okay. But of course, again, right, I can emphasize this enough. The operation to go from here to here is going to fall on the x, because you take expectation of the x. And then the out, sorry, any question? the outer layer, right? Let me just do this. The outer expression is on the y. So on big Y. Okay. The reason is because, you know, after you do this, right, the result after the sum is going to be an expression of y. So okay, let me say this again. It's not really on the y, okay? It's on what? It's on this guy right here. It's on that function of y. But basically the focus on the y, the x has disappeared. If somehow when you perform the outer layer, there's some x remaining, whatever that means, you just know that you're wrong, okay? It just cannot be there. But you're performing it on this expression, which is an expression of in terms of y. But then, so you sum over all possible value of this expression with what kind of probability? Well, this is a function of y, so it takes on certain values with probability y equals to that value. You understand? And what is this expression? Well, it's this, right? So, yeah. That's that expression, right? Times that. Well, what do we observe? We observe that, right? This guy can go inside because this is sum over x. If it goes inside, it cancels, right? So we got this. What else? We can switch the order of the sum, right? And if we switch the order of the sum, the x can be factored out as the constant in terms of y. And if you sum over the y like this, you just get the marginal, right, probability, which is probability x equals to x, which of course is x. You understand? Any question? Okay. So I said I will do both continuous and both discrete. I will skip the both continuous case because it's just exactly the same idea. Instead of writing probability, you will write density, and so same calculation. I will not waste our time on that. Okay, you can read the textbook or write the proof yourself. I will rather move on to problems and examples and things like that. Any question? So let's look at problem. So what quiz are we on? Quiz 5. So that's the question number 20. So we have 3 coins. So each of them, right, have probability of head to be 1/4, probability of head to be 1/2, and then probability of head to be 3/4. Okay, so these are three different coins. They're not all fair coins, obviously, right? Some of them, right, only gives probability of head as 1/4, 1/4. Some of them gives probability of head as 3/4, whatever. So a coin is chosen randomly among these three and continuously flipped. All right. Question A, find the expected number of flips until first head. How do we do this? So this is one of those examples, right, where you have to condition on something. I'll rather call it easy, because what you need to condition on, right, is kind of obvious. But so let me say, right, in general, the theme of a lot of questions, okay, in chapter 3 and forward is to use this formula to find expectation. The challenge are twofold. The first one is to find y, the appropriate y. Appropriate. All right. Because this formula is universally true. Whatever random variable you condition on, it will always come out as expectation of x. However, in terms of human computation, if you choose the wrong y random variable to condition on, you'll probably have no idea what this is. Or this might be easy, but you won't be able to perform the outer calculation. Who knows? But to find the appropriate y is in my opinion, the hardest thing. Okay. And I can't tell you how to do it. It's really a combination of intuition, experience, understanding the problem, etc. But even so, but after you find the appropriate y, of course, then you have to perform the calculation. And again, right, let me emphasize, there are two layers here. The first is to compute conditional expectation, which, right, may have to resort to finding the conditional distribution, okay, before you can find the conditional expectation. And then you can compute the outer layer expectation. Okay. They're all, let me say, non-trivial steps. But here, right, if you let x denote the number of flips until the first head, it's kind of easy because what should we condition on? we should condition on which coin we select, right? That's it. So here, right, 1, 2, 3 obviously denote the first coin, second coin, and third coin that we select. Okay. So just to elaborate, right? For example, if you select the first coin, then clearly, right, because probably your head is 1/4, you are gonna fall under the category of geometric 1/4, etc. You understand? And therefore, right, the short answer here is it's gonna be, right, 4. So expectation of x given y equals to 1, right? Sum of expectation x given y equals to I, right? I equals 1 to 3 times probability y equals to I. So that's going to be, right, 4 plus 2 plus 4/3, everything times 1/3. Any question? Question B asks to find the mean or expected number of heads in the first 8 flips. How do we do this? Once again, right, here the obvious random variable to condition on is, well, which coin, right? Because if we know which coin, then we will know, you know, what the probability is, right, of head. So for example, if you let x be the number of heads in the first 8 flips, notice, right, again, this is a coin randomly selected. So x given y equals to 1, right? If we select the first coin, then it will be binomial 1/4. Sorry, 8, right, 1/4. X given y equals to 2 will be binomial 8 1/2. X given y equals to 3 will be binomial 8 2/3. Sorry, 3/4, right? Okay. right? The formula says expectation of x will be expectation of x given y, which will be, right, the sum, because y can only take on 3 values, which will be, you know, this is 2 plus 4 plus 6, everything times 1/3, whatever that is. Any question? Okay. So now let's move on to some, let's say, slightly less obvious choices. So quiz 6. So here we're going to go back to the classical example of a geometric, right? Let x be a geometric p random variable. Compute expectation of x, all right? By conditioning, let's say. Conditioning on an appropriate y. So again, right, the key is to find what to condition on. If we flip, right, a coin until we see the first head being probability P, and we want to find the average value, what information will be valuable for us to condition on? Here, it's intuitive that we let y be the result of first toss, first try or first thought, whatever, right? Meaning that, right, you try to find the number of tosses until the first head, or let's just say, right, is 1 of zeros. You try to find the first ones. So, right, how many trials until you see the first one? 1 with probability P. And so, right, you know what? Let me just switch back to head and tail just to make it easy. So tails, 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 right? Whatever, and then heads. So y right here will be 1, right, if first try was success, right? And 0 if failure. So what is the conditional distribution of x given y equals to 1? Well, if the first trial is a success, then the number of trials to get to the first success is just 1, right? Identically 1. On the other hand, if the first trial is a failure, then what? What's the distribution? Well, if the first trial is a failure, then you basically wasted 1 trial. And then you just repeat the process. Okay? Now, a lot of times, as you will see, the X we're looking for doesn't have a nice name to it. So another notation I will write is this. Okay. What this means is that condition on certain things, the random variable we're looking at will be certain value, add with a copy of it, right? So X tilde is just a copy of X, but in terms of distribution. Okay. Again, right, it's very important that we do not add X back, because that's nonsense. X cannot be 1 plus X. Okay. So basically, we're saying that if the first trial is failure, then we lose 1 trial and we repeat the same experiment. But of course, right, we already lost 1 trial, so the original count is not the same as the next count, but we're just going to repeat by saying that we want to look for, right, the first success again. Okay. Anyway, right, so then applying the formula, right, what do we get? It will be, right, expectation of x given y equals to 1 times that probability plus expectation of x given y equals to 0 times that probability, right? So the first step of identifying the appropriate y is done. Now the computation step, right? Now we have said, right, that if y equals to 1, then x equals to 1, so expectation is p, 1. On the other hand, if y equals to 0, then we wasted 1 trial and repeat the process. So this is expectation of x plus 1 times 1 minus p. And of course, right, the left-hand side is expectation of x. Okay, any question about this? And this is actually what's very common in this kind of problem. you set up, right? More, it's like a recursion, if you will, right? But basically, by conditioning on the appropriate random variable, whatever you're looking for will reappear in some form. The process will repeat itself in some way. So therefore, you have whatever object you're looking for, expectation or the variance on both sides. So you have an equation that you can solve for, right? Here, well, 1 minus p plus p is 1, right? So you got something like expectation of x is 1 plus 1 minus p times expectation of x. But if you subtract this expression on this side, you get p, right? There you go. So that's the proof. I mean, one way to do it, that the geometric p has expectation 1 over p. Any question? Okay, let's continue. Now, a generalized version of this will be as follows. As x be a so let's say we have independent trials, right? Or coin toss, whatever. A coin with probability of has to be p. Okay. Let x be the number of trials until the first 2 consecutive successes. Find expectation of x. Okay. So first question, we understand what x is representing. Is x a negative binomial? Is x a negative binomial? What does a negative binomial represent? Well, a negative binomial, right, represents the number of number of trials until you see the first 2 successes. But, right, these 2 successes do not have to be consecutive. That's a key word here, right? Consecutive. So in other words, right, if you look at negative binomials, then besides the 2 successes, everything else is failures. On the other hand, what we're looking at here, right, is whatever it is that somehow has 2 heads next to each other. First time. In other words, previously you could have a head and then you can have a head again. But you never have a head together, 2 heads together before that time. And a number of trials to get there, right? It's a question. Okay, and we're looking for expectation of number of trials to get to that. So again, right, the theme here is to condition. What random variable should we condition on? What is y? The answer is let y be number of flips until the first head. Okay. Why is this an appropriate random variable to condition on? Notice, right, if you condition on the result of first flip, it won't help here at all. Result of first flip is irrelevant in this question. I mean, you can still condition on it, okay? And it will still be true. Whether you let y be the result of first flip, like the previous question, or the number of flips until first head, the formula works. But you should see for yourself that if you let y be the result of first flip, it's just unclear how the number of trials until the first two consecutive successes is related to the result of first flip. It is related. It's just the relationship is not that nice, so it's not something we can write down very, very easily. Okay. And again, this is exactly where the difficulty, okay, of choosing y comes in. But anyway, right, if you let y be the result of first flip, then what is x condition on y? Well, so you see here, for example, right, if this is how many trials for you to get to the first flip, then, right, from there, you can easily get two consecutive flips, right? Sorry, two consecutive heads, meaning it's just one more flip if, right, the next flip is head. In other words, this is with probability P. All right. Otherwise, what happened? Otherwise, right, if the next result is a failure, then you cannot get a consecutive heads, right? Then basically, you wasted all your chances. So consecutive two heads, right? Basically, if you get one head and the next one is a tail, then all your chances have been wasted because you will not be able to get two consecutive heads. Meaning that if the next is a failure, then you have to restart the whole process again, which is y plus 1 plus x tilde with probability P. And this is exactly, sorry, probably 1 minus P. And this is exactly where the notation x tilde, right, is useful because, you know, I don't think this has a name, right? At least it's not something well known or well named. So just number of trials into the first two consecutive successes. So just might as well write x tilde, okay? All right, so that's a very important step to write down, to be able to analyze. And of course, to identify y. Any question about this? So this is the conditional distribution, right? Sorry. This is a conditional distribution of x given y. Any question? Then of course, right, the next thing is expectation of x given y, right, which is 1. Well, clearly it takes on these two values, right? Notice y is a constant. So expectation x given y will be y plus 1 times p plus, right, y plus 1 plus expectation of x, because x tilde and x have the same distribution, times 1 minus p. Okay, so far? All right, then, right? So notice, right, this is exactly also where you have to pay attention. The first expectation falls on the x, keeping y as constant. Falling on the x means you hitting the x tilde here, right? And of course, because x tilde has the same distribution as x, it comes out as expectation of x. And then the second layer, right, is when you hit it with the y. But, right, what is expectation of y? Y is number flip until the first head. Therefore, y is geometric. P, right, random variable. Therefore, you got 1 over p plus 1 times p plus 1 over p plus 1 plus e of x times 1 minus p. Meanwhile, right, this is exactly also expectation of x. So you see, right, the same theme happens. Expectation of x, the object to be that they're looking for, appears on both sides of an equation, and you're solving for it. But again, right, to get there, you have to find the right random variable to condition on. You have to write down the right computation, etc. Any question? But, right, of course, we can see this simplifies to what? This is 1 over p plus 1, 1 over p plus 1, or p plus 1, right? P1 minus p. So this is 1 over p plus 1, right? And then plus expectation of x times 1 minus p. Subtract over here, you got expectation of x times p is 1 over p plus 1, or expectation of x is 1 over p plus 1 over p squared. Any question? Let's try one more time, right? This is quiz 8. Let x be the, so you still get a coin flip, right? Probably head is p. Let x be the number of flips until you get 3 consecutive heads. Okay, you can say heads if you want. Find expectation of x. Okay. So again, right, we want to find the appropriate random variable to condition on. So what is it? What should we condition on here? What is a random variable to condition on? The answer is, well, for the previous one, you want to find the number of flips until you get a first head. So here, it'll be the number of flips until two consecutive heads. Okay. Why would that be appropriate? The reason is, right, the moment you get two consecutive heads, then you can analyze the next flip to decide the result of your experiment. That's why this is the appropriate one to condition on. Okay. Right, and x given y is, you see, one of the proof that is appropriate is the analysis here will be exactly the same as the analysis here. Meaning, right, once you get two heads, two consecutive heads, then it will be y plus 1 with probability p. Because once you get two heads, right, whatever that is before, then the next one, if it's a heads, then you're done. Otherwise, you just start again. Now, I warn you, right? If you do this problem these kinds of problem too many times, it almost is a knee-jerk reaction to say it restarts. Yeah, kind of. But a lot of times the trick is to be able to carefully write down the condition for it to restart. Not all random variables, right, after your condition restart in the same way. I don't know how to tell you, but basically this one, right, you have to really think about why I am very confident or I say it correctly that, right, if the next one is a tail, then the experiment will refresh itself. Okay. The reason is sometimes you cannot decide that the experiment refreshes itself after the next step. You might have to look at the next two steps to decide if the experiment refreshes itself, etc. So it's not simple. Okay. So don't build that into, like, again, a formulaic thing that, oh, after one step, the experiment got a refresh. Not guaranteed unless you understand clearly what's going on. But in this case, yes, it works that way. And so the calculation goes exactly the same way. Okay. The only difference now is that before, when we calculate expectation of y, right, we say y is geometric p, so therefore expectation of y is 1 over p. But, right, now y is the number of flips until heads. So we have to build upon the previous calculation. So the x in this, right, is the y in that. What I mean is, right, this is 1 over p plus 1 over p squared. You understand? But, right, the simplification is the same. This is this times P, this times 1 minus P. Therefore, it's just 1 plus 1 over P plus P squared, and then plus expectation of X times 1 minus P. And then, of course, write the left-hand side expectation of X. Subtract therefore, expectation of X here is 1 over P over P squared over P cubed. All right, any question? All right, let's conclude this with a general question then. Let X be the number of flips until n consecutive heads, right? N equals to 1, 2, 3, etc. What's expectation of X? The answer is 1 over P or P squared. When do we stop? 1 over P to the n. Okay. And if you ask to prove it, how would you prove it? You will prove it by induction. What are you inducting on, or what are you inducing on? So induction is done by conditioning on the number of flips until n minus 1 consecutive heads. Right? That's what we've been doing previously. Okay. Any question? All right, so remember, right, that the exam is on Friday. So it's 80 minutes. You'll get 5 minutes, okay, to do the whatever facial recognition, identity check, etc. So I do believe, right, that leaves 35 minutes to start for you to ask questions, etc. So my calculation may be off, but something like that. I'll make an announcement there, and then you'll see, right, what the exam time is exactly. Basically, you have 85 minutes, well, plus 10, right, at the end for submission, but that's extra. So 5 for setting up the equipment, 80 to do the exam. Again, right, if you take more time to set up the equipment, that's on you, okay? You should have done it beforehand. If your responders results do not pass certain kind of requirements, well, depends on the case, right? We'll have to kind of see what happens. But, well, short answer is please follow all protocols, right? So that we don't have to take any further actions beyond that. Most importantly, right? Show your work area. Just think, right, that someone looking at you, would they have any doubt that you're doing something else besides taking the exam? If not, we're good, right? But if there's some doubt, it will have to be resolved somehow. And let me tell you, right, your exam result will be in question. If it's too good to be true, etc. Okay. So anyway, so I'll answer your questions if you have any. If not, Friday will be exam. I'll be on office hours, right, for the first 35 minutes or so. Okay, I'll see you then.
Hello, Professor.
Yeah.
Is exam including chapter 1, chapter 2?
Mhm.
No chapter 3, right?
No, 1 and 2.
Okay, thank you.
Mhm.